we're going to be looking at Young's modulus. The definition of Young's modulus is stress divided by strain, or stress per unit strain, or the ratio of stress to strain. And the units of Young's modulus is given by the units of stress divided by the units of strain. So the units of stress, pascals, and strain has no units. So that means the units of Young's modulus is pascals or newtons per metre squared. Now you know stress is force divided by the cross-sectional area, and you also know strain is the extension divided by the original length. If we were to substitute both these expressions for stress and strain into the equation for Young's modulus, we'd get force divided by area, which is our stress, divided by our extension divided by our original length, which is our strain. Or we can show it like this, where it's our stress divided by our strain. And remembering, if you divide fractions, you can times them, but then this side will be turned around to become L over E. So we can see that this equation simplifies to FL divided by EA, and how I remember it is FLE, which equals Young's modulus. So this equation you don't need to remember because it's given on the formula sheet, but it is the definition of Young's modulus. This equation is not given, so you probably be good if you can remember it, and as I say, a good way of remembering is think of FLE, F-L-E-A, and that equals Young's modulus. We're now going to compare the force constant and Young's modulus with three different spring situations, combinations. So first we're going to look at a single spring on its own, which has a force F applied to it. So the original length of the spring without force F was L, and then we're applying force F, we get an extension E, and the cross-sectional area of the spring is given by A. So force constant for this spring is force divided by the extension. The stress for this spring is the force divided by cross-sectional area, and the strain for this spring is the extension divided by the original length. And if we was to find the Young's modulus for this spring, it would be our FL divided by our EA. Let's now consider two springs which are connected in series, and you have a force F applied to them. So now the original length of the spring is going to be 2L, and applying a force F to these two springs will give an extension of 2E. The cross-sectional area of the spring has remained constant, so it's the same A. So to find the force constant, it's going to be our force divided by our extension, so it's our force divided by 2E. So what you can see is, by having the two springs in series, we've got, if we compare it with our one spring, we've halved the force constant. So considering the stress for these two springs, it's going to be our force divided by the area, so that's remained the same as the one spring. Now considering the strain acting for these two springs, well, that's our extension divided by our original length, so that's going to be 2E divided by 2L, so that gives us our E divided by L. So you can see that the strain has remained the same compared to the one spring. So if we've got the same stress and we've got the same strain, the Young's modulus is going to be the same. And if we use this equation but applying the values that we have for the two springs in series, so we've got F, and then our L, our original length is now 2L, divided by our extension, which is 2E times A. You can see that the 2's cancel, so we're left with our original FL divided by EA. So again, it's showing that the Young's modulus has remained the same. We're now going to consider two springs, again similar to the springs we had here, but now connected in parallel, and we've got the same force F being applied to them. So in this case, the original length of these springs are L. The extension is now going to be a half of the original extension, because each spring is taking half of the force. So if they're getting half of the force, they're only going to be extending by half as much. The cross-sectional area, because they're now these two springs parallel to F, you've got a total cross-sectional area of 2A. So if we consider the force constant, that's our force divided by our extension. So force divided by E divided by 2, and that simplifies to 2F divided by E. So if we compare this with what happened originally with our single spring, we can see now our force constant has doubled. Now considering the stress, which is going to be our force divided by our area, so that's going to be force divided by 2A. So again, comparing that with the original of our single spring, you can see that now our stress has halved. If we now consider the strain for these two springs, so our strain is our extension divided by our original length, so that's going to be E divided by 2 divided by L, and that simplifies to E divided by 2L. And if we compare that with our original strain, you can again see that the strain is halved. So we've got half the stress and half the strain, but that doesn't mean that the Young's modulus is halved, because Young's modulus is stress divided by strain, and as both has halved, that means they cancel out, so the Young's modulus has remained the same again. And again, I can show that again by applying that FL divided by EA formula, but using the values we have here. So we have F times L, our original length, divided by the extension, which is E divided by 2, times by the cross-sectional area, which is 2A. So you can see here we've got E divided by 2 times 2A. So the 2's cancel, so we get the original expression we had for Young's modulus, FL divided by EA. So what you can see when we're comparing the force constant and the Young's modulus for these three spring combinations, you can see that the force constant changes when you change the original length and when you change the cross-sectional area. But the Young's modulus has remained the same, so it's a constant. So it's independent of length and the cross-sectional area, the dimensions of your material. It will still give the same value. So the force constant depends on the length and the cross-sectional area, whereas Young's modulus is independent of the length and cross-sectional area of the material and so remains constant. Both these values relate to the stiffness of a material, how easy it is to deform a material. And so when comparing the stiffness of the material, it's best to use the Young's modulus value because it's a constant for a material.